Now we will move on to solve a simple problem using the differences, the finite differences we've learned so far. And we've learned 4 finite differences so far: backward, forward, central, first order differences, and the second order difference, which is a central difference. Good. So this is the equation we're going to solve. F of x is 2 ln x, that's your function. We're going to use this table we're given, and we're going to find the first and second derivative approximations when x equals 2. So basically you can think of it as filling up this table with f prime of x and f prime prime of x, but only at x equals 2. So these are the values we're looking for. We're not interested in this. So we're looking for f prime 2 and f prime prime 2. And we're going to use the differences we've learned. But before we do that, let's find the analytical solution so we can compare our numerical solution to it. So analytical solution is what we're doing first. And so this is f of x, right? So what's f prime of x? The derivative of that is 2 times the derivative of ln x, which from calculus is what? 1 over x, right? So this is basically 2 over x. Done. So given that, what's f prime of 2, which is what you're looking for, right? It's 2 divided by 2. Whatever x is, put 2 in there because this is f of 2. So 2 over 2 is what? 1. So that's the answer for the first problem. To get the second problem, we need to first find f prime prime of x. Now we already have f prime of x, right? So if we differentiate this once more, what's that going to be? It's basically 2 times 1 over x. So what's the derivative of 1 over x? We keep 2 out because it's a constant, right? What's the derivative of 1 over x? It's minus 1 over x squared, right? That's your calculus. And this is precisely 2 over x squared. So what's f prime prime of 2? Plug in 2 wherever you see x in the equation. So it's 2 over 2 squared, which is 2 over 4, which is 0.5. So that is the analytical solution for this problem. Minus 0.5, so this is minus 2 over 4 actually. It's minus. So minus 0.5, 1.0. Now we're going to solve the same problem, but using numerical method. So we're going to use the finite differences we just learned in previous videos. So we've already been given a table of 3 points, and you remember we were given 3 points in the discussion. So this first point, this is what you're looking for. You're looking for values at x. So this is x, where x equals 2, right? That's what you're looking for. So easy to see, this is going to be x plus or minus delta x. It's minus, it's before that. And the last one is x plus delta x. So when you have this, you already know if you use forward difference, f prime of x with forward difference is going to be what? You really need to know this equation by heart, right? This is what we learned from high school calculus, right? Divided by delta x. So this you should know by heart. It's forward because this is forward relative to your x. And now, what's f at x plus delta x? This is x plus delta x. So this is f at x plus delta x, 2.19722. Minus what is f at x? This guy, 1.38629. And then you divide that by what? By delta x. What's delta x? This minus this, right? Which is same thing as 2 minus 1, which is 1. So I'm not going to find this difference for you. You can do that in your calculator, and I'll later show the result. I believe it's 0.81. Or you can calculate that. Then the next one is backward. So this first order forward difference. We'll do the same thing now backward. So what's the equation for backward? Right? We derived this before two ways, graphically and from Taylor series as a backward difference. So what's f of x? This is x, right? At 2. It's 1.38629. What's f at x minus delta x? X minus delta x is here, so it's 0. Minus 0. What's delta x? Same thing. 2 minus 1 is 1. So that's your result for the backward difference. It's 1.382. How does it compare to the exact solution? The exact solution is the analytical solution. This is 1.0. This is 1.38. A little bit off. Actually, far off. 38% off. This is like roughly 0.2% off. All right. How about the central difference? Central difference, of course, for first order. So first order central difference was what? It was f at x plus delta x. Again, you have to know all of these, right? Very easy to remember. Divided by what? 2 delta x, because you skip 1 point. We derive this in two ways, right? Graphically and from Taylor series. So let me leave some space for writing the derivatives. So what's f plus x plus delta x? This is x plus delta x is 2.19722. What's f at x minus delta x? 0. Right? What's 2 times delta x? Delta x is 1. 2 times 1 is 1. So this divided by this is what? A little over 1.08, right? Leave you to do that calculation yourself. And now you see this is closer to 1, suggesting that the central difference, is more accurate than the forward and the backward differences, which we have discussed before. What's the order of accuracy of the central difference? Order what? Is it delta x? No, it's delta x squared. These other two are order delta x. We discussed that in the derivations. And that's what you're seeing with a numerical example. And we'll do the last one we're going to calculate is f prime prime of x. And remember the equation we derived. Who remembers that? X plus, what's the next thing? Plus or minus? Minus 2f of x. Then plus something similar but at x minus delta x. Then you divide all of that by what? Is it delta x or 2 delta x? Or delta x squared? You divide by delta x squared, the square of delta x. I keep putting it in parentheses so you don't do delta of x squared. It's delta x all squared. Good. So just substituting the values. My pen isn't writing anymore. Oh, it's actually writing in white. Let's see. So what's f at x plus delta x? This x at delta x 2.19722 minus 2 times what's f at x? 1.38629 plus f at x minus delta x, which is 0 plus 0. All of that is basically this, right? You can forget about this one. And we're dividing by the square of delta x, which is 1, right? So 1 squared is 1. So really, we don't care about this either. And we just need to take this difference, and whatever you get is the final answer. and it's close enough to minus 0.5. It's minus 0.5 point something. You calculate it, and I'm going to just show the results in the next few slides. So everything I worked there is what you see here, right? So this is the forward, that's the 0.81. This is the backward, the 1.38. This is the central, which is closer, it's 1.09, right? More accurate, closer to enough to 1. Then the central difference, which I just did now using this equation, is minus 0.57, close enough to minus 0.5. And now, what if we use a smaller interval? Because the other interval was 1, right? Now the interval is 0.1. So you're going to see the effect of truncation error, how truncation error changes as delta x increases. You recall that truncation error was delta x for first order finite difference, and for forward and backward first order differences, and for central it was delta x squared, right? And so we repeat the calculation, which I wouldn't go into details, just do exactly what we just did now. But here we're focusing on the central difference, right? Which is the one that's order delta x squared. So you plug in that here, which is this, minus this other guy, right? Divided by 2 delta x. That's the equation for central difference. See how close it is to 1. Central, for the second order difference, which is also a central difference, this is the equation we wrote out before, but you're using this value minus 2 times this value, right? That's what this is. F of x plus delta x minus 2 f of x plus f of x minus delta x, and you're divided by 0.1 squared, because that's delta x squared, and it's spot on minus 0.5. So your results are more accurate as delta x increases, which lines up with the original definition of your derivative, that your discrete derivative, say delta y over delta x, tends to dy dx in the limits where delta x tends to 0. So as delta x gets smaller, it gets more accurate. And this, the exact solution, was what we got from the analytical solutions. So all of this lines up with the fundamentals.